To determine whether a vector field is conservative, we actually have a test that can be performed. Let's look at an arbitrary vector field where the first component is a function of x and y, the second component is a function of x and y. And what we'll see is that if this vector field is conservative, then the first partial of the first component with respect to y is going to be the same as the first partial of the second component with respect to x. It's also true that if these first partials are equal to each other, that implies that the vector field is conservative. When the left-hand side of a statement implies the right-hand side and the right-hand side of the statement implies the left, we call this an if and only if scenario. And the symbol to represent that is a double-sided arrow. But in this video, we're just going to focus on showing that the left-hand side implies the right-hand side. So we begin by assuming that this vector field is conservative, and if f is conservative, then there's going to exist a scalar function f at x, y, such that the gradient vector field is the same as the given conservative vector field. And again, this scalar function is considered to be the potential function for that vector field. At the beginning, we said that this vector field has the components p, which is itself a function of x and y, and q, also a function of x and y. And since this is a conservative vector field, this can also be expressed as a gradient field. And the gradient vector is first partial of f with respect to x, first partial of f with respect to y, which is also p and q, and I'm going to drop the functional notation for the sake of simplicity. So this means the first partial of the potential function with respect to x has to be the same as the first component of the vector function, and the first partial of the potential function with respect to y has to be the same as the second component of that conservative vector field. So first partial with respect to x is equal to p, first partial respect y is equal to q. Now let's rewrite this using the curly D notation, which says the first partial of the potential with respect to x is equal to p, and first partial of that potential with respect to y is equal to q. Now let's take this equation and differentiate both sides with respect to y, and on this equation let's differentiate both sides with respect to x. So we'll take the partial with respect to y of this equation on both sides, and the partial with respect to x of this equation on both sides. So we end up with the second partial derivative of that potential function with respect to x first and then with respect to y is equal to the first partial of p with respect to y, and then the second partial of potential with respect to y first and then with respect to x is equal to first partial of q with respect to x. Now let's rewrite these second partial derivatives with the subscript notation, which is partial with respect to x first and then with respect to y. This is equal to partial p respect y, and we'll leave the right-hand side with curly D notation. Over here, on the left-hand side of this equation, we have the partial of the potential function first with respect to y and then with respect to x, again, leaving the curly D notation on the right-hand side. Now, if you'll recall, fxy is equal to fyx by Clairaut's theorem, which then leads us to partial p respect y is equal to partial q respect x, which is what we were trying to prove. And this is a quick test that can be performed on a vector field to determine whether or not it is conservative. Then we can start trying to find a potential function for that vector field.